when we thought of Dasara lecture series, there were several things that we need to address. And one of the most important was to identify eminent scientists who can speak to children. We approached Professor Ajit of ICTS, Professor Nagasuma Chandra of IISc, and Professor Ranjani Vishwanatha of JNCSR to help us. They very helpfully, they gave a lot of time to us. We had several discussions, and because of which, clarity emerged on the theme, the number of lectures we should have, and the target audience and all that. I'm very thankful to all three of them for all their guidance in organizing this. This idea of having Dasara lectures originated when COVID-19 was rampant. Like all institutes in India, we also had funds crunch. We approached chairperson of Infosys Foundation, Srimati Sudha Murthy. She readily agreed to fund the program, and she was very supportive and very graciously granted funds for organizing this event. I'm very thankful to them also. Today, we have with us Professor Rama Govindarajan of ICTS, an eminent scientist. For our today's lecture series, I extend a very warm welcome to you, madam. We have with us many eminent people. My senior colleague, Dr. Shailaja, is here. I extend a very warm welcome to her. I extend a very warm welcome to all of you who are present here, who have made time to come to this program. Now I request Madhusudan to introduce the eminent speaker. Thank you.
So we are extremely pleased that Professor Rama Govindarajan is here with us to give the second talk in the Dasara lecture series. So we had the inaugural one yesterday by Professor Tarun Savadi. So Dr. Rama Govindarajan is a professor and dean academic at the International Center for Theoretical Sciences, Tata Institute of Fundamental Research, ICTS in short, which is in Bangalore. So before joining ICTS, Professor Rama Govindarajan worked at Jawaharlal Nehru Center for Advanced Scientific Research, JNCSR, and she was a scientist at National Aerospace Laboratories, NAL. She did a PhD from IISc and postdoc from Caltech. So her main research interest is fluid dynamics, and that's the reason why she is speaking about aesthetics in fluid dynamics. When you spend a lot of time working in a particular field and you become an expert in that field, then you not only see the nitty-gritty and the finer details of the subject, you also learn to see the aesthetics in that, the beauty that is inherent in the subject. And we are extremely happy that somebody who has put decades of work in fluid mechanics should be speaking about aesthetics in fluid mechanics, and we are all very eager to listen to you, to your talk, Professor Rama Govindarajan. So just to continue with her introduction, quickly, she had her BTech Chemical Engineering in IIT Delhi. I felt this is interesting to tell because chemical engineering and fluid dynamics are at least at the outset, on the face of it, not related disciplines at all. So it's very interesting to see how these two are related through her research work. And she did her PhD in aerospace engineering, which is something absolutely important in fluid dynamics. And she did her postdoctoral fellow from Caltech, California Institute of Technology. And she is a recipient of Bhatnagar Prize in Engineering, and she is a fellow of the American Physical Society, Indian National Science Academy, Indian Academy of Sciences, and National Academy of Sciences, India. So a very distinguished speaker that we have with us today. So once again, a warm welcome to you, madam.
Okay, first of all, a big thank you to the planetarium and to Dr. Madhusudan for this opportunity. I'm very happy to talk in front of all of you. So how many of you have studied any fluid mechanics? Many of you. Okay, so basically for those who have not studied it, a fluid is something which is not a solid. That's as simple as that. It could be gaseous or liquid, or it could be toothpaste or anything. And yeah, in the case of toothpaste, we worry about whether it is indeed a solid or a liquid, but yeah. So, and the dynamics of these things is the aesthetics of which we are going to be talking about today. And I put whether serious or having fun, there's aesthetics in it. So you could be doing some very worrisome subject like climate change, or you could be just enjoying yourself with fluid mechanics. So in both of these cases, you will see aesthetics in it. And I want to just portray that. If somebody has a question, just raise your hand or start talking. There's no need for me to complete everything. If you get bored, we can stop, and it will be more fun to talk about things as we go along. So everybody, please feel free to stop me. So these are eddies in the ocean. So this is like, eddies around in the Bay of Bengal. Basically, eddies are things where fluid is going round and round. It's as simple as that. So, and this is actually a simulation. This is actually come from satellite data, whereas this is a simulation. I think that is the Japan coast. So you see these very large eddies all the time, and it looks beautiful, right? So you can look up Earth Null School to see what eddies are there right this minute. You can go and look at that. So these are just two examples of things which look beautiful. How many of you know about the Kármán vortex tweet? Okay, nobody. This is a very interesting thing. So what happens, suppose I keep like a round ball, like I keep this bottle, and wind is flowing around past it, or water is flowing past it. So suppose a river is running and I put this bottle there. Behind the bottle there will be these eddies. So the flow will come in this pattern that you see here, and there will be rotational motion like this. So it forms a very beautiful pattern, a very beautiful vortex street it's called. It's basically a street. Whenever I refer to vortex, I mean something that's rotating. Some fluid that's going round and round. So it's circulating in this pattern. Okay, so why is this interesting? It's because, see, this is an island, Selkirk Island, okay? And the ocean flow is going past the island. And because the ocean flow is going in that direction past the island, this vortex street is formed. You can see, right? But what we are seeing is a pattern in the clouds. So the island is not as high as the clouds. This is the remarkable thing. The island is here, the clouds are there. So how do the clouds know that there's a vortex? And how are they arranging themselves? You're seeing this in a satellite view. So that's an interesting thing. There is a theorem which I won't explain now called the Taylor-Proudman theorem, where because the earth is rotating, a lot of these things become stationary in they become like a two-dimensional. So if there's a vortex at the ocean boundary, that vortex extends till the sky. So like all of these vortices are extending, and the island is on the ocean surface, but you're seeing this vortex street in the cloud pattern. Okay, so there's lots of these interesting things. One of the important things is that most of the time, whatever fluid mechanics is going on, we can't see it. We don't see it, so we don't know how much fun it is. For example, there's 5 fans in this room, and they are circulating air in a very turbulent motion. So like if I could see it, I'll see vortices everywhere. I'll see circular motion everywhere, but we don't visualize it all the time. And just to give you an idea that fluid mechanics is across all the scales. Like when I understand something about fluid mechanics, I may be understanding more than one thing because I'm understanding a fundamental principle. So these are microorganisms, and that line is 1 micron or something like that. And this is a galaxy, so we know it's very different from 1 micron. But there also you see the spiral vortex in the galaxy as well. So very similar things are happening at all kinds of scales. Sometimes the physics is different and sometimes it's not different. So this is just to give you an idea of the beauty of it. So today's talk is about patterns. So I've written, wherever you see a pattern, think of us. Think of our group, because we looked at instabilities which create patterns. So, like you've all seen many of these patterns, right? Is there anything new that you haven't seen here? Anyone?
That cloud pattern.
This cloud pattern you haven't seen? Okay, so for this cloud, this is called the Kelvin-Helmholtz instability. It's a very special instability. We'll talk about it in the next page, next slide. But you will see it in the sky if you pay attention. On calm days, you will see it in the sky if you pay attention. And it's just forming because two layers of fluid are moving at different velocities. So like this one is moving fast, this one is moving slow. So they're rolling up the cloud. As they go on, they're rolling up the cloud. So that is one thing. This is just like a Kelvin drop, we call it, like how a drop, with this kind of shape falls from a tap when you open it. I mean, you have to have a pretty viscous fluid like honey or something. This one I'll show you a nice movie of this droplets splashing. This cloud we are going to talk about, Mamata's cloud we'll talk about in some detail. I just put an elephant's trunk there, you can argue that it's not fluid mechanics. But I put an elephant's trunk there to give you an idea that wherever you look at these things, there is a pattern. Everywhere there is a pattern and there is a length scale. There is a typical length associated with it. Now this trunk thing is interesting because look there, like those wrinkles of this elephant are far apart from each other, right? But when you look here, they're closer to each other. So the length scale is a function of some length in the problem itself. So wherever the elephant's trunk is fat, you get these big wrinkles, and wherever it's thin, you get smaller wrinkles. So like if you're looking at the Mysore festival, check for this, for all the elephants. Any tree that you see will have these patterns. This is columnar basalt, it's called, it's a rock formation. And this is just a bartan, it's kept on a heater, and some, you can put some salt or some coloring, and as this thing heats up, you can see these cells forming, and if you have some solid in the bottom, it will get solidified like this. So you will get very interesting patterns in things that you heat up. In milk also you will see these patterns. So the thing that I want to tell you is, like, does anybody have any idea how these patterns come? That is the thing that I want to tell today. And by the end of today, you should have some idea of why it forms a pattern. In particular, this sand thing, right? Like, everybody's seen this kind of thing on a beach, right? How many of you have seen a sand dune? Yeah, you've seen a sand dune. So sand dunes are some exaggerated limit of non-linearity of this problem. Now it's interesting that, like there is sand. Technically, sand should like being flat, right? It should like to be flat because that minimizes potential energy. I mean, why should it occupy hilly regions where the potential energy will go up? So it's sacrificing something by doing this. That's one point. Next thing is, like, each grain of sand is an independent guy, right? Like, it's not tied by sellotape to the other grains of sand. So how does each independent grain of sand know where it should be in the pattern? Like how it should sit in the pattern to make a global pattern. So obviously it's not got any knowledge of this, but still you're getting these beautiful patterns, and the length scale is very, very typical. So even for a great distance, things are organized in this thing. So what I've shown here is that why is there a pattern? That's the basic thing I want to answer here. So with this slide, if you you'll get an appreciation for why is there a pattern. So the idea is that it's a thing of instability. How many of you have heard the word instability? Lots of people. You've seen things like this, right? Photos like this, where if you have a ball on top of a hill and a ball in the bottom of a valley. So the top of the hill ball is in an unstable equilibrium. It's still an equilibrium. At that place, there's no force acting on the ball, right? But if you move it a little bit, it will start rolling down. So we call this one unstable and we call this one stable, right? So that's exactly what's happening in the fluid. The interesting thing is that sand pattern I showed you, right? That sand pattern, the flat one is unstable. The flat one is unstable whenever there's a wind. And the only stable pattern is the one with the waves. And why does it make those perfect waves? That's the next question, right? So now, like, I could take this ball, I could move it slightly from its position. I could move it slightly from its position, and I'll ask if that disturbance is growing or decaying. So I can write the maths for that disturbance, and I'll ask, is it growing or decaying? So that disturbance can be, you can do what you call a Fourier transform. All of you know Fourier transforms? So you can actually break it up into different waves. I can take any disturbance. Remember, this is a fluid, so there's disturbance in space and time. I can take any of that and I can break it up into contributions from many different waves. Because it's a tiny disturbance, I can do that. So then I'll get like this wave plus this wave plus this wave plus this wave. I'll get waves of all wavelengths. And for each wave, I'll ask, does it grow or decay? So the interesting thing is, for certain wavelengths, it will be stable, and for certain other wavelengths, it will be unstable. So if I put a particular wave into that particular kind of disturbance, that thing will grow. So the flat sand has this particular wavelength which grows. And then it will reach this place, and then it will stay. After that, it won't make a big mountain because the wind is fairly gentle. It will reach what is called saturation. It will reach some height and stay saturated. So tomorrow also, if I come back, if the wind was steady, I'll see the same sand pattern. Tomorrow, if the wind direction changes, I'll see a new pattern. Or if you jump on it, it will take some more time for wind to make that pattern again. So this is why, like, you often see patterns in nature. This is a fundamental reason why you see patterns in nature. The fact that there are, any perturbation consists of sums of different waves, and some of them, some special ones of them become unstable. So the Kelvin-Helmholtz happens when you have a flat surface in the sky, below it is a different velocity, and above it is a different velocity, and together, like, whenever there's a velocity difference, it becomes unstable to certain wavelengths. And that wavelength gets selected and you start seeing the cloud pattern. That's a very famous instability called the Kelvin-Helmholtz instability. And this is a calculation of that same Kelvin-Helmholtz instability. See, we saw it in a cloud where the wind was like not perfect. But suppose I run a simulation with the exact same equations. I know Newton's laws for a fluid. Newton's laws are called Navier-Stokes equations in a fluid. If I run it perfectly with two velocities, I'll get this very beautiful pattern, which is because density difference. Right now, the velocity difference gave you Kelvin-Helmholtz. Density difference will give you some other kinds of instabilities, very famous in fluid mechanics. So these are some double diffusive. This is an actual simulation of the Dead Sea. How you see salt collecting. So salt is not uniformly distributed in the ocean. There's more salty, less salty, more salty, less salty. So all this white color is more salt and all the blue color is less salt. So that's interesting, right? I mean, like in tea, suppose we're making tea at home and then I put sugar in and mix it nicely. Then any mouth I drink will have the same amount of sugar, right? I won't have patches which are very sugary and patches which are not sugary. And this is a big ocean which is being mixed by the wind. So many things are happening. So isn't it interesting that salt gets arranged like that? So this kind of pattern happens everywhere and under certain circumstances. So everything that you think in a simple-minded way, like if you have sand, it should sit in a flat way, it should not do these wave things. Or if you see this thing like salt should be uniformly mixed, it should not be arranged in this beautiful way. This one is a simulation of the Dead Sea. So Dead Sea is very, very salty, we know, but salt fingers are seen in every ocean. And this one is actually a lab wala. This one is actually made in the lab, the salt fingers. It's made in a dabba of this size. So if you understand the instability, you can actually make it in a small dabba. It's basically fingering. So it's very easy to understand. And then we know that in nature there's always some disturbance. Nothing will be perfect, like there will be some disturbance, some wind, something, and it's going to put lots of waves in this. So now if there's heavy fluid sitting on top of light fluid, and if I put a perturbation like this, then what will happen? This region is heavy and this region is light, right? So I've got a wave where some part is heavy and some part is light at the same height. So the heavy guy wants to come down, right? And the light guy wants to go up. So I can get two things. One is it can come down like this, come up like that, and I can get a vertical structure. Or it can go vertically down and this can go vertically up. And I'll get fingers. So in the Dead Sea, some combination of these things is happening. And you can actually do calculations which give you these answers. You can do some of these calculations with pen and paper. You don't need some fancy computer. Of course, like if I solve the whole thing on a computer, it will look like an experiment. I'll get very good answers with that. If you had a fast camera, this is what you'll see in your kitchen. You don't need anything very dramatic except a fast camera. And if you can play that again, look at that very characteristic next thing going up. If you can play that again, I want you to focus on the pattern. And even that exact pattern you can do calculations. And that is an instability. That wave has got selected and it's becoming non-linear and you get this special pattern. Okay, so that is a combination of surface tension and normal gravity and other forces. So there is first the inertia of the fluid. You push that drop from up there, you drop the drop. So that drop can now energize some of the fluid which was sitting still before that. So this drop is coming and a whole bunch of other fluid gets into motion. And because of that, like they are, very energetic right now, so they convert that kinetic energy to potential energy by rising a bit. So now that they rise, surface tension hates that. Surface tension says you guys should stay flat and I don't like this extra surface area and all. So it will start pinching them off into droplets. So you will get all those very neat droplet pinch off. And then like at the end that energy will get dissipated. Because you have viscosity in the fluid. So like it will get dissipated. It's like, if I switch off my mixie, you're making juice in your mixie. If I switch it off, it won't rotate forever, right? In like a very short time it will stop because fluid has viscosity. So it will get dissipated and everything will come to a standstill. And where did that energy go? In the form of heat. So like when you drop that droplet, you've actually heated up the water by a little amount. In the end, when everything is still. So you see this very interesting thing which happens with just a drop splash. First you had this. You had sand here and air here. Agreed? And it was a flat interface. So we know that's an equilibrium solution. Okay, we know that's an equilibrium. There's no net force acting on it. But then there's wind going above the sand. Now that wind like perturbs this thing. So all kinds of perturbations come. So I'll get a general perturbation of the sand which looks like this. It won't look like a pure wave. It will look like dirty and messy in the beginning. So in that dirty, messy disturbance that the wind has made, and that can be broken up into waves. Like in a linear system, it will just be an additive sum of different waves. So like I can Fourier transform it, or like the sand in its wisdom does this. So it's made up of a combination of waves, each with their own coefficient. And that can be a function of space and time. Okay? So for a given bunch of space, you will have this thing. In that, like that will be made out of all such waves. And this wave will be stable. In this case, this big perturbation wave will be stable. So that will die off. So even if the wind is putting a perturbation, that will exponentially decay. Okay, only a small band of wavelengths will be unstable. And that will exponentially grow. So at short times, it selects that particular shape. That's why you're getting a very special pattern. It will select it and those will grow. And then after some time, like potential energy will win. Potential energy is not going to allow this, pokey mountains of sand. Like it will win and you will get something of this height. And then it will stay there forever if the wind is steady. If the wind is steady, it will reach one new equilibrium state, which is the pattern state, and it will stay there forever. Okay, so this is called crow instability. This is another thing you can see with your naked eyes. So like every time a plane flies on a clear day, now monsoon, don't look now. Look in November or something. So like you will first see those 4 vortices, right? The trailing vortices which come out of the aircraft. Now after some time they become 2, like the 2 things on each side, they merge with each other and they become 2. And these 2 vortices, like one is spinning this way, one is spinning that way. It's just what is coming out of the, the trailing, it's coming out of the wingtip. So you have 2 wingtip vortices which are coming out like this, they call contrails. And then like these 2, you'll expect them to just go in a straight line, no? But being in a straight line is not stable. It's not a stable equilibrium for those vortices. So only like becoming a particular wavy pattern is stable for those vortices. So then like if 2 vortices are like this and they will get perturbed like this.
You're getting that?
And then that perturbation thing will turn by 45 degrees. So they'll get perturbed like this. You're getting that? And when it grows and grows, the bottom part of the 45-degree plane, right? They'll start touching each other.
So
the thing will pinch off and it will make rings. No. You can make in the lab 2 identical vortices and you will always see it. You'll get an even better ring in the lab. This is in the air where some wind can be blowing it, something else can be happening. You will get a very neat one in the lab, yes. The thing that Rahul did is, this is a Crowley instability, very well known, we're going to talk. He said, let me not take balls, but let me take ellipsoids. So actually in the lab he 3D printed some little discs and he put all the discs in a line and asked them to go down. And he asked what's going to happen. Now the interesting thing is when 2 of them join together, right? When 2 of them see each other, they will interact and fall faster. The drag in the middle will be less than the drag on the sides. So it will start falling faster. So if 2, and if you put 2 at an angle here and here, they'll start falling faster in this direction. So now if I have 3, like one slightly down, one here and here, they'll come towards each other. So that will become an instability. So that is the famous Crowley instability and Rahul did something with ellipsoids for that. Please go to the next slide. Yeah, so basically he showed how it need not always be the same story with ellipsoids. So this is the dabba we have in the lab and here's, you see that instability? You see that, right? They're not falling at the same speed. And they're choosing a wavelength. We can make it choose some wavelengths. We've done some cheating to make it choose some wavelength, but yeah, we can do that. But we didn't ask some of them to fall faster. So and later you see this clumping, like some of them have come close together and they've made this instability. So all instabilities are slightly counterintuitive. You can run the bottom one, which is a special case which happens only with ellipsoids, not with discs. No, the bottom one. Yeah, you can just run it. See, this one is less willing to make big clumping, but you can see the wave. So we can do these calculations for different, it's also an experiment from the dabba. We've just put these tails to make it visible, that's all.
No, I won't.
Any questions on this? Yeah, so the point is for spheres, any number of spheres in a line is unstable. Even if there are 3, it's unstable, it will clump and come together. Up to 2, it will follow a standard path. Once they come nearer and nearer, they start falling faster. It's like a bigger ball, like they are effectively like a bigger ball and their terminal velocity will increase. So this is happening in spheres. We have a slightly different story with ellipsoids, that's all. And it's mathematically very interesting, which I won't be explaining today, which is why we did this. Like why ellipsoids come out different. And all this exponential growth stuff I told you about doesn't hold. Mathematically, it's a different kind of growth. Okay, so like the few examples I could come up with, and maybe you guys have better examples. One is this, when they make fertilizer, right? Or they make milk powder for babies or even for grown-ups. So you are putting all these milk drops from the top, you will have a big chunny like with many holes, and these milk drops are all falling down and they will be drying as they fall down. So imagine if they all clump up. And then it will become really bad, right? So like it will be nice if we understand how to stop that clumping. That is one thing. Similarly, when they make fertilizer also, liquid comes down and it solidifies into little pellets. And other things like that, maybe volcanic ash when it falls. There's like, you can do this calculation with different separations between the discs. Different separations and different wavelengths of the perturbation we fed it. So like in this case, he just had that dabba, right? Like you see the top thing where the discs are released. We just have like, little slots in which these discs sit. And then like Chadwa has a comb which is this big and he'll just press the comb gently. And these things will fall into the silicone oil. And the beauty is you don't need a fast camera because if I put it now, then at night only it will reach the bottom. It's so very viscous, these things will be coming down very slowly. And they make these beautiful patterns. Just as they come down, you can sit in the lab and watch. It's not some rocket science experiment, it's just oil and particles. You put these particles in oil and that's all. You leave them and you'll see the patterns. And so, I said we cheated a little bit, right? So like what we'll do is once in a while we'll remove one thing or we'll move it slightly. So like if I want a wavelength like this much, I'll move one particle to the next slot. And then I'm selecting that wavelength. Pehle se I'm giving a perturbation which is rich in that wavelength. So then that wavelength gets selected. Some of those are unstable, some of those are stable. And if the distance between these is very big, then they're all stable. So we've done those calculations and we know how to put it. So this is just to show that there are patterns at all scales, and this one I want to boast about it, so I put it here. So like some 20 years ago I had written a paper where I said that even at slow flows, if there are two fluids which mix with each other, let's say salt water and sugar water, or some two kinds of things which mix with each other, then these two fluids under certain conditions will form waves. They won't go in a straight line, they'll form waves. And this year, these people in Paris, they found that exact thing. They found those waves. So this is just a preliminary experiment result. We've not written the paper or done anything, but exactly like, was predicted that under these very special conditions, you can get these waves for low speeds. We got them. That's all there is. So this is just like one of my favorite kitchen things is chocolate. Who's made chocolate at home? You made chocolate at home. And do you remember these type of things when you pour it? They're really beautiful, right? And if you guys are nice to me and give me a treat, I'll give you the recipe. You can make like very good, waves and things with solidifying chocolate. So I'm just showing that to show you that what happens in lava flows, everybody knows lava, right? Is not too different from chocolate, like at least visually it's not too different. If there's some new science, like we'll find out. So this is this special lava called hoe hoe, like it's hoe hoe. So you should go and find out what it is. So that's why they put an apostrophe there. I'm not going to tell you more about it because I've forgotten the linguistic origin. But yeah, you see these patterns in rocks. Do you see that, in this one, for example, it's so beautiful, right? So cool. You have these big patterns, and remember, these are big structures, like not chocolate in the kitchen. But this liquid lava is coming out and it's solidifying in these forms. So like extremely big structures who are made like this curved thing. And you look inside each curve, what do you see? What do you see? Crescent troughs. Do you see there are rope-like things? So it's like a braid, right? Not the flame. See that picture, that one. You see, like rope-like things which are making up the big structure. So there's some sub-braids in it. In this one, it's even more clear. Like there are some big, it's almost like a rope which is twisted inside and then twisted here. Yeah, do you see this? The lines. Yeah, and this is just another structure. So they form these amazing structures, which is why I was trying to ask the planetarium to make this experiment. If we can do this experiment, it might be fun. So the next one. So yeah, these are turbulence, like you may not always get patterns because of instability. It can go to, I mean, many wavelengths can be unstable, some very big mess can happen. So patterns are one thing that happen due to instability, and like all of these are examples of turbulence. You can go to the next slide. Yeah, this is a plume from Mount Etna. This is a very turbulent plume, you can see, no? It's a very messy and disturbed plume. Do you see the size of this? Like look at those kuti things which are big houses. You see that? So this plume is that big from this volcano. So like volcanic ash and things are very important problems, like how, you know, these things spread, how pollutants spread across continents, across things. And like you take any climate problem, you have to do fluid mech. How many of you are worried about the climate? Everyone. Who's not worried? You're not worried? You didn't show your hand, you're not worried? You are worried. Okay, great. So everybody is worried about the climate, right? We need all you young people to solve climate problems, to see how we can, you know, use fluid mech, use our knowledge to mitigate things, like at least help ourselves in a little way. There's many things we can do to mitigate. And we need climate warriors. We need young people to, you know, really help in this. And it's time to not worry about what are the other people doing. It's time for each of us to do something for it. So this is just some turbulent structures. This is a golf ball, this is some, I don't know what ball, maybe tennis ball. So this will be the vortex structures, you can see if you could see it. So just beauty in fluid mech. And if I just take this table and I blow wind past it, I'll see these horseshoe structures, very beautiful structures, if I could see it. So just if I had a table fan and I put it, and I could color the vorticity, I will see that. So a lot of times we test aesthetics in fluid mech, but it's invisible aesthetics. And there is one very interesting new kind of cloud called the Asperitas cloud. So for many decades, nobody found a new cloud. And this is a new cloud designated by the World Meteorological Organization. And this is the explanation they've given. So this is this Asperitas cloud. Now, lucky thing is, before 2017, there was nobody knew about Asperitas. It's designated now. So when we started working on this problem, there were only 2 papers on it, which even mentioned the word asperitas. So we could try to see what instability causes these bulbous structures and these things. So you could go to the next slide. Yeah, it happens because of these droplets coming out of the cloud and evaporating. So you can go to the next one. Equations we solved. Next one. What happens is, as these droplets fall into the dry air, they will evaporate. And when they evaporate, they let out latent heat and this layer starts cooling. So I told you heavy above light is unstable, right? You'll get these waves or you'll get some pattern. Now you're creating heavy above light just by droplets falling and evaporating. Yeah, these are different simulations we did and different shapes we got. So you can compare, like almost every mammatus cloud we're able to produce in our simulations. So we seem to have understood what is causing it. These are that asperitas I told you. We think it's just a mammatus when the wind is blowing like this, when there's a wind shear. So you get these patterns rather than the vertical patterns. Next one. Yeah, this movie you can show. Because of the wind, you get a predominant direction. We are trying to mimic these clouds. So it's very turbulent, but still there's a broad pattern. That's the interesting part. You see, no? We're able to mimic some of these clouds. We wrote our own code. We wrote our own program to solve it. Fortran. Yeah, Fortran is the best for these things because MATLAB will never be fast enough. We want very big grid, We want many, many grid points. We're solving differential equations on every grid, whole bunch of differential equations. The size, this one was like 256 cube. Of that order. We did 512 cube also, different things like that. Sometimes 1024, but on that side we'll have fewer, like that. You can't do it on MATLAB. Yeah, so I want to end by saying that, science is a very, very nice activity. So if you all want to do science research, I'll recommend it very highly. Because see, like you all the time work with young people. Every year you get new, young and very bright people to work with. These are some of my PhD students who are all faculty in other places, or they have jobs like Gayatri's in Airbus. So like these are people who've gone out of the lab, and from them I've learned so much, and from me I hope they learned something.
So I'm sure that she has convinced all of us that fluid mechanics is inseparable part of our lives, both animate and inanimate. She has given ample examples from both worlds to show that fluid mechanics is so important to be studied. That's a big motivation, especially considering that there are budding scientists sitting here. It's a fodder for thought, seriously to think fluid mechanics as a subject of your lifetime research. So thank you very much for this inspiration. And the final part is, I request our director to promote to hand over a memento, a token of appreciation to Professor Rama Govindarajan.
Thank you. Thank you so much. Thank you so much.